Okay, hello everyone. I hope you can hear me. Thanks for that warm welcome, Steve. So I'm a member of the Advanced Technology Group at NetApp. You can think of it really as a laboratory, but we're not allowed to call ourselves a laboratory because we're supposed to be a little bit more product focused and less blue sky thinking. But you know, that's the function we perform. We keep an eye on technology trends and try and keep the firm and its products relevant, say 3 to 5 years out. I have to do this, I would imagine. And this is sort of the way we go about it, really. Just going to give you a flavor of how we do things. I'm not going to say anything probably groundbreaking or insightful or anything that you don't know already. What I'm really going to do is give you an idea of the perspective of a company who's actually trying to stay in business in this incredibly fluid environment. Because I would argue that the storage business today has never been more fluid. There's a lot of opportunity and a lot of threats out there. So really, it's just sort of how we view things, and that's the value I think I'll bring today in the talk. But you'll have seen all the technologies and things that I've identified in this talk. So the way we go about it is we interact with a lot of different entities. We go to academic conferences. We form relationships with universities. We have a good relationship with UCSD and Steve. We talk to our partners. What's really important, vendors. Right? They show us their technology 3 years before it's released. We sign NDAs, we're not allowed to talk about it. But it gives us a leg up. We can start to prepare for it, incorporate it in our products and that kind of thing.
So when you get an NDA from a company, when they say in 3 years we're going to have a hard drive that can do X,
yep.
do you then go to your customers and tell them in 3 years we're going to have a server that can do X based on the NDA information from the...
Provided that's a legal landscape that one has to be very cautious when navigating. But if we don't name names and name products, et cetera, if there's just a capability that we believe is going to come, then yeah, we will tell customers about it. But we will not violate the NDA in doing so. And of course, before you go and tell, but the thing is, when you go and tell customers stuff based on an NDA that a vendor has shared with, and information a vendor has shared with you, if that vendor doesn't come through and that 1 petabyte hard drive that fits in your pocket never made it to the market, then you look foolish when you go and speak to a customer. So one has to be terribly careful when engaging in that sort of behavior. We watch what our customers are up to, et cetera. Depending on what we learn there, we analyze and try to put together and build a big picture and try and identify areas where we need to act and move forward in various ways. It might be as simple as writing a report. Maybe we'll start building a prototype or something. And then this is key for a company, right? You need to get patents to protect your IP, intellectual property. Maybe spin off a startup or something. Papers are also important. It's good for the company to be seen in major fora and venues to make it look like we're on top of things. Inspires customer confidence. Customers will quite often, you just can't say you're an innovative company anymore. Customers will actually come in and want to talk to us. We've got to tell them what we've got planned 3 years from now. And if they don't think it's innovative enough, they'll lose confidence in us. So that's really important. It's not just the stuff we sell today. They want to know what we're thinking and where we're going. You need to stay on top of things. So in this particular tech trends, I'm not responsible for all these slides, by the way. This is something we take around, including our executives have seen this. So this is sort of the prism that we're looking at the landscape at the moment. And we've sort of classified it into these 4 areas and how they intersect and how they're going to impact the industry. So the talk is going to be divided up into 4 major silos. I'll start off talking about some hardware trends, move on to applications, the data center, clients, and then I will summarize with some conclusions. Okay, so IBM introduced the hard drive back in 1956. It's a lot bigger than anything that you can imagine today. It used a lot more power, the sort of power that one could only imagine before OPEC was a force to be reckoned with in the world. It was very, very different. But at the same time, the basic principles behind it are still in operation today in all of our hard drives. And for 50 years, the hard drive landscape has been fairly stable. It was pretty easy to predict what was going to happen. Areal density kept going up by a very predictable curve. Interfaces might come and go, but it was a fairly stable landscape. From the business perspective, though, it did change in the sense that these guys, they became commodity and they became ubiquitous. So back when IBM introduced this, and this is important from a storage company's perspective, right? Back when IBM produced this, the value they added and the margins they got away with charging on this device was on the hardware. The hardware was where the value was. Today, hard drives are a commodity. There are only 2 manufacturers left in the world, really. IBM divested itself of its hard drive manufacturing in the last decade. The margins were just too slim for it. It doesn't play those games. Today, the only way you can make money by selling hard drives is by adding value, right? So at NetApp, we sell hard drives. We package them up, and we put a controller in front of them, and we charge what we feel are very reasonable prices, but we do mark them up. And the only reason why customers pay those prices is the value we add. They're not paying for the hard drives. They can go and buy them for themselves. These are like oranges now. They're like orange juice. They're probably disk futures on an index somewhere. So it's very difficult to make money just by selling hard drives these days. But around 2006, even. Pardon me?
Why do you sell hardware?
So that's a very interesting thing that I don't know if I want to discuss in front of cameras, but believe it or not, there is actually, if you listen to the hallway in NetApp, there's actually debate about whether or not NetApp is a hardware or a software company. I would argue until the cows come home that we're a software company. That is where our intellectual property is. That is where all of our intellectual property is. We don't care which hard drives we use. We're always sourcing them from both vendors based on a number of different factors, right? But our value add is our software, and we could take any box and put our operating system on it. That is our value. We're a software company. But there are still people inside NetApp that argue that we're a hardware company, even though we use commodity hardware and just assemble it. So I think it's a matter of perspective. We are starting to move away from that. We are now selling virtual servers, appliances, VSAs. So if you want a NetApp filer, you can just install software inside the cloud. I think people are worried that if we went to purely software, it would change our business model dramatically and reduce revenues, and they're afraid of cannibalizing the hardware business. Yeah, so disks have changed a good deal since 2000. For 50 years, it was fairly stable, but starting in the last decade, disks started to appear and look very, very different. There are more of them. They're specialized. It's crazy. So the first big difference that emerged, right, was the difference between personal and enterprise storage devices. The top-end disk that goes into NetApp Filer or our EMC VMAX is very, very different from the disk. Well, they don't have disks anymore, do they? But some of you might have some notebooks there with disks in them. Completely different. The disks in desk-side computers are completely different. It's not just the interface. It's not just the difference between fiber channel and SATA, right? The read error rates are an order of magnitude at least worse in personal storage devices. Write error rates are at least an order of magnitude worse. The engineering that has to go into making this thing spin at 15,000 times per second means the materials and all sorts of other things are completely different. Personal storage devices typically spin at 5,400 RPMs. Sometimes you see at 7,200. The media is even changing now because for those people who just didn't think the areal density was growing quickly enough, right? We have shingle drives. So shingle drives now, the sectors are starting to overlap. So they're packing more bits into the sector density. You can read the data back pretty much as you used to, but writing is now very, very, very slow. You have to read all the neighboring sectors in as well as the sector you want to write, and then rewrite them all back together. So you're getting density, around 25% more density, but you're paying for it in rewrite performance. So guys like iTunes, they love this stuff. It's denser. They spend most of their time reading. They don't care that much about writing, so it works for them. But do you want to run Waffle on that? for those who don't know, the proprietary file system in a NetApp filer is called Waffle. So do you want to run Waffle on that? I don't think so. I don't think it would work very well. Now we've got these object drives. These are basically, I didn't list it down with the interfaces down here. This is, really interesting, right? So these new kinetic drives from Seagate, they actually have Ethernet interfaces built right into them. So you take your hard disk, put it on your network, and you can use a RESTful interface to just read and write objects. The guys at CMU who were doing this stuff 20 years ago aren't that impressed. But, this is now on the market, and you can buy it, and we don't know how this is going to affect our business or how we should use them or if we should be using them. Spin down disks. Archival storage is becoming very, very hot. If you look at something like Amazon, right, they have their normal S3 storage, but they also have Glacier storage. Really, really, really cold storage where they charge 0.0001 cents per gigabyte or something like that. We actually spent a couple of months figuring out how they could do that economically, and we're not convinced they're making money or breaking even, but if they are, they're using something like spin-down disks, shingles, and tape combinations. So basically, spin-down disks are designed for the disks to be turned off most of the time and to be powered back up. It's not as easy as it sounds. I'll talk about that more in a couple of seconds. And finally, these interfaces just keep proliferating as well. Though some are starting to die, right? Fiber channel is starting to die. SCSI, I guess, is hanging around a little bit in there. But people don't want those 15,000 RPM fiber channel disks anymore. They don't care. Flash is just makes so much more sense to them now. And even SATA in the enterprise, I remember back in 2002, customers didn't understand the difference between enterprise and personal storage disks. And they kept demanding, well, we want SATA disks, they're half the price. And we kept explaining to them, you're going to lose data, you're going to lose data, you're going to lose data. And they said, we don't care, we don't care. And if we didn't sell it to them, somebody else was going to. So we started selling them. And people started using them in ways they promised they wouldn't. It was supposed to be fast backup initially. They'd sign documents saying that's all they'd use it for. Then they'd call up and say that their mission critical DB has just gone down because their SATA disks went south. Well, even though they violated their service level agreement with us, we still have to support them and fix them because you want to keep your customers. And the customer is always right if the check clears. So I just want to talk about hard archive disks for a second because they're kind of interesting, and I don't really know what to do with them yet, to be honest. We're certainly not going to run Waffle on them. But they're kind of interesting. So the typical hard drive lasts maybe 3 to 5 years, and you can power cycle it maybe 30,000 times. So these new archive disks, right, that you can actually power cycle them 300,000 times. But it comes with all sorts of caveats. You can only do 200 terabytes of I/O on the things in total over its lifetime. Right? So for a 4 terabyte disk, right, or a 5 terabyte shingle drive, you can only read the entire disk 45 times, and then it's done. So this is definitely just for backup, right? You only read the thing when you recover it and that kind of stuff. It's going to spend half of its life doing absolutely nothing. It's doing about 2 megabytes per second of I/O. These are really, really cheap disks, but for something like archival storage, where disk spinning burns electricity, right, and lots of other things, this is really important. So for 50 years, this is sort of what the landscape looked like in the storage world. DRAM was the most expensive medium, but it had by far the best latency, right? And then down here, it's fairly simple, right? Backup, tape, it's the cheapest you can possibly do. It's a pain in the butt to get your data off of it, but it's cheap, you get what you pay for. And then, in the disk space, it's fairly simple, right? You have enterprise disks, and you have personal storage disks, and you don't want to use a SATA disk for performance critical stuff. You'd never see this in an EMC VMAX or something like that. It was pretty easy to get your head around it. But it's just so complicated today, I don't even know where to begin. And we need to play. Do we need to play as a company? Do we need to play for all these media? What do we do with it? it just keeps changing all the time, right? Even Flash is constantly moving around. Samsung's about to come out with their three-dimensional flash arrays. They're stacking the NAND gates to increase density, keep driving the longevity of that technology. Capacity flash is an idea that's beginning to get a lot of notice. In particular, eBay really wants this. If you're a flash vendor and you see the telephone ringing and you see it's from eBay, you don't answer the phone anymore. You just don't want to hear it. Had enough. They're really getting a lot of pressure from guys like eBay because they want a completely solid-state data center. Completely solid state. And there are some games you can play with Flash, right? So if, forget the SLC stuff. If you use the 3D Flash stuff and you dial back all sorts of stuff like the reserve that you need to get decent performance so that more of the actual Flash itself is available for the capacity. Tune it so that it's a little bit slower to read and write because you don't care about how many times you get to read and write it. All sorts of games you can actually play. It's not as crazy as it sounds, but it's not there yet. But capacity flash is something that I think is going to be very interesting because most people think of it today as being exclusively in the IOPS tier. Disks, I can't even call it disks anymore now. We're calling it nearline and archive. Cloud storages, right? Customers now expect their on-premise data to migrate seamlessly to and from an off-prem cloud back into their data center. All supposed to be happening automatically based on policies. People are still using tape. You cannot believe how many people are still using tape. In fact, I wonder if Amazon's Glacier is using tape. Their service level agreement is that they'll recover your data within 10 hours or something. That's enough for somebody to get in a van, drive to Utah to the big warehouse, look up the tape, drive back, and put it in a machine for you. And SCM, storage class memories. These are going to, I think, start appearing before the end of the decade in real numbers, real volumes, in serious products. There's a lot of players here, right? ReRAM, STT-RAM, blah, blah, blah. A big one, though, is phase change memory, PCM. I can't say everything from NDAs and stuff like that I've seen, but I think PCM is going to be a basic part of compute infrastructure by the end of the decade. And it's interesting stuff, right? Because if you look at storage, if I just draw a little line there, everything over here really, it's all block oriented, right? There's a real clear distinction between where the computation takes place, today it's in DRAM, and where persistent state is maintained. It's two separate worlds. It's a memory hierarchy. But with the advent of SCM and what Intel is calling NVM, non-volatile memory, and by that they define that as any kind of storage medium that can stall the processor on a load. So that's how they define it in public, right? So what someone can extrapolate from that is they're going to put PCM or something on the memory bus. It's going to be on the motherboard. And when you think about it, it makes sense. If you have something like PCM, which has read latencies of 25 to 50 nanoseconds, and it's got write latencies of up and around 200 nanoseconds, you don't want to put a bus between you and that memory. You do not want a PCI, even express bus between you. You're talking about a microsecond of overhead when you can just use unprivileged processor load and store instructions to get to your data. That's what you're going to do. So you're going to have to get the kernel out of the way, and you're going to have to get that data into user land because that's where the latency is going to be best. And people are going to want it, and people are going to do it. It's inevitable. I know I'm not saying anything too controversial here, but with NV heaps and stuff like that. So as a storage company with all this new media, we're really trying to understand what we're going to do with all this stuff and where it fits in with our products and our customers and what's going to be in the enterprise and what's going to be exclusively in consumer stuff. And there's all sorts of new spaces in the memory hierarchy. But one thing I do want to call out here, right, is reliability. which is old person's talk for, is the data really there and is it correct? I think it's called durability. There's all sorts of words for it now, but we used to say reliability. And we know how to do this in the disk world, right? Starting at the lowest level, if we at NetApp, we reformat disks. They're not 512 byte sectors, they're 520 byte sectors. And we use that extra few bytes to put in checksums. Then you can do it at the block level. Then you can do it at the file level. And then you can do it at the RAID level. There are multiple levels where we're going to catch incorrect data, detect corrupt data, and quite often even correct the data. We know how to do this. It's well understood. We've been doing it for decades. But if you start putting PCM on the memory bus, right, and you have a memory controller that's just accessing it, and you don't want the processor to stall while you're doing stuff, how do you do things like verify that the bytes you just read from that PCM are correct? And that they don't. ECC, as you get it today in servers, is nowhere near good enough. I think it can detect 2 to 4 bits of incorrect data, and it'll do it automatically. But that's just not good enough if you're talking about terabytes of enterprise-worthy data like your bank account. So something is going to have to be done there. It'll probably require hardware support because it's going to have to be done very, very quickly. But this is a very fruitful research area. Getting that right, that will be huge. Because when you're talking about the volumes of stuff that we are here, mistakes are going to happen. When I used to, at my last job, I used to do my computation in 6 different data centers simultaneously. And we would get ECC errors. We were using, for everything we used IEEE doubles, which is 8 bytes. And we would, at least once every couple of months, we would get a wrong price or a wrong risk number, and we'd go and it was an ECC error. It happens. And you've got to catch it. If you don't care about it, horrible things can happen. We were using the Andrew file system to distribute the models to the machines, the individual machines inside the data center. And bad binaries would slip past the Andrew checksumming stuff all the time, at least once every 3 months. Andrew would screw us and give us a bad binary because it snuck past the checksum. So getting this right is going to be really, really important. Archival disks. You've got data sitting there for months, years, without the disk being turned on. Is the data on that disk correct? Is anything in that data center correct? Was there an X-ray event or something nearby? How we store data in the long term is a very fruitful research area that hasn't even been, the surface hasn't even been scratched yet.
That's why I'm surprised anybody still uses tape.
Yes, so am I. But then again, I routinely see COBOL applications still, so I don't know. Yes? Pardon me?
Because in that case, you have some media that stay the same.
Yes, if you believe forever.
Well, if you have some range of error, like in your data, like you're writing 10, 20 grains, the outliers of that standardization is so high that you can keep for years.
But even if the half-life is 25 years, some data will be incorrect after 1 year. Not half of it, and you've got to detect it. But I mean, it's another technology that will be used, and people will have to find a way to use it. Okay, applications. This is another space that has just gone wild in the past 50 years. The number of interfaces that are being used by applications for storage have gone up. It's gone up a great deal, right? You've got graph interfaces, key value stores, RESTful interfaces, objects. There's just tons here, and the types of applications are also exploding. You've got real-time analytics. You've got data mining, or big data, whatever you want to call it. You've also just got day-to-day, computation. When you build a business now, you don't just hire a COBOL programmer. We'll get into this a bit later, but there's 10,000 applications used to produce an application nowadays. It's extraordinary. And it's what's making this all possible and driving it, right? It's platform as a service frameworks. If you want to start, any one of you that wants a startup, I would imagine that your first prototype would be in the cloud. You'll probably get an Amazon EC2 account, right? That's where it's happening. So this proposed programming model and interface for PCM and other stuff that I was talking about earlier being proposed by SNIA. But before I talk about this, I want to know, just a quick show of hands, how many of you know who SNIA is? That is at least 3 more than I thought would. So, my point here is that, so SNIA is coming up with this elaborate programming model, but the one that's going to win is this number 3 one here, right? So as I was talking about earlier, if you put PCM on the memory bus, and you can access the stuff with unprivileged load and store instructions, and you've never heard of SNIA, are you going to use this programming model? No. So I would argue this entire SNIA exercise is probably irrelevant. They don't realize it. They're living in a world where SCSI type protocols, and that's what they're used to specifying. They're enforceable and controlled by hardware and privileged instructions. They're just not used to operating in this world. What I just said would be incredibly controversial in some other venues, but my point really here is that none of you have heard of SNIA, and so I don't think this, and you don't need SNIA to actually use this hardware, so I don't think this this programming model is going to go anywhere. But basically, the idea here is that if you have PCM on the memory bus, right, you should just be able to use the map to map that address, to map that memory into your process's address space, and then you can just use unprivileged load and store instructions, and you're going to persist your data. There's no kernel intervention in this world. And that has real ramifications for us as a storage company. Storage guys have been standing in a forest for so long, we haven't seen a tree in years. And this is what I mean by that, right? We're used to this world, okay? Applications today, when you're going to write a program, right, and you want to choose a data structure that you're actually going to perform the computation on, do you think B+ trees, and do you think tables and stuff like that? No, you go look at what you need from the STL. If I need log and lookup, I use the map. If I just want a FIFO or something like that, I'm going to use a standard list. And that's how I actually perform my computation. That is what applications actually want to do. But at some point, PowerPoint is doing this as we speak. But at some point, the state is going to have to be persisted, such as my presentation, right? So the program is forced by the storage system, because the storage system is a cruel master. It is forced by the storage system to actually completely change the representation of its state to make it work in a good way with hard disks, because they're mechanical, right? It's called serialization. When you write your data out from memory onto disk, you change its format to work well with a disk. And that could introduce bugs. And going the other direction, reading it back in, again, you have to change the state from the disk to the disk's format, to the actual format that you want in memory. Application programmers hate doing this. It introduces bugs, it's more code they don't want to write, they hate it. Nobody wants to do it. Okay, but once you actually have written it out, the data is going to be sitting inside a buffer cache here. And then at some point, a page daemon in the kernel is going to write this data out and clean the buffers. Now today, NetApp plugs in at the protocol level, right? We have an NFS client, we'll mount one of our volumes and write its data out. And because of the way the kernels work today, a number of important things are masked from us, right? We just see a stream of blocks. We don't actually know which bytes in those blocks have changed, because it might just be a subset of them. We just know that that block has changed. We don't know when that buffer has changed either. We just know generally, probably within the last 30 seconds, something in this 4K has changed. That's because the kernel can only see change data at the granularity of a page. It just sees a dirty bit for a 4K page. It doesn't actually know what has changed inside the page. So, imagine if this was if this wasn't DRAM, if this was PCM, I don't need to do this anymore, right? If I don't need to do this anymore, the buffer cache and the NFS client isn't important anymore. So, where does the filer plug into this world if this is now persistent? Well, we're probably going to have to plug directly into the application in user land. What's more, we just can't stream bytes across. We can't just stream NFS blocks across anymore. We actually we only want the actual bytes that have changed, right? So consider, inserting a node into a doubly linked list, right? If the two nodes that I'm interposing my new node in are on separate pages, I'm just modifying a couple of bytes in each one, right? The pointers, and then I'm going to write maybe 80 bytes for the new node in the interposed page. I've dirtied 3 pages, but really I've only written 100 bytes. So I do not want to send 12K across here. I only want to send the 100 bytes. So you need a new protocol, and you need a new library. And nobody is going to write an application that works just with NetApp filers. So this protocol is going to have to be standardized, because it'll have to be an open standard that everybody can implement, because nobody is going to want to tie themselves to NetApp. They're going to want.
Why would I build that system? Because I have this memory over here, which is my PCM memory is 200 nanosecond memory.
Yep.
And you've got a 10 microsecond network between me and my filer. So I've just effectively taken my 200 nanosecond memory and turned it into a 10 microsecond memory.
You're going to have to play all sorts of funny games. So you're assuming that a couple of things there. First of all, the speed of the network. Right? We're actually expecting new networks to pop up in the next 2 or 3 years that offer significantly superior time. But you're dead right. Yes. You do not want to run a transaction that is... you can buffer things here and fill Ethernet frames, and it can keep up. But this guy will always be a little bit ahead. So there's a window of failure. But the window of failure isn't that scary if you remember that this is persistent. All you're really doing is making a disaster recovery copy in a different failure domain. And not everyone will even need to do that, right? Lots of people are happy with one copy of their data today, in which case, yeah, they don't need to do that. But your comment is spot on. What do we sell in this world? Right? Now, the one interesting thing about this model is, so let's go back to examine what Steve just said a little bit more carefully. Right? So we could have that world here, and this is persistent, so I don't really care anymore. I'm not going to write anything out. The kernel is just going to see dirty pages. And then it can just stream blocks out, but there'll be so many changes per block, hopefully the cost will be amortized over them. In which case, this is going to be a very cost-sensitive capacity tier, right? NetApp sells high-performance filers. Are you going to spend all that money on a very expensive appliance if you just need something that's going to stream data slowly, right? You don't. This is our chance to remain with a high-performance filer that people want to buy otherwise. You don't need one, as you said.
So why do you think we need PCM to do all of this? You seem to think that PCM is going to be the main driver for people to move to this model. But
well, you
build
need
an application in DRAM and,
because DRAM's ephemeral.
If you're a filer, then there's durability that way.
Well, because it's not durable, right? If you actually care about your data, right, it's in DRAM. Yeah, but then your application can only run as fast as 10 microseconds.
They have battery backup DRAM or ways to.
How much of it though, right? The filer uses battery backed DRAM
right.
for.
So you guys already use battery backup DRAM to.
For very small quantities, it's expensive.
I mean, application DRAM sizes aren't that large either.
They're tens of gigabytes, even terabytes.
Okay. I mean, how long does it take for that? I mean, I'm sure you could build a battery to do that. I'm just saying that.
Oh yeah, yeah. No, it is interesting.
I think that PCM doesn't necessarily have to be the only driver for that.
Yeah, no, you're perfectly right. And in-memory computing is doing that today. I'm going to get to that later. But you know, you've got to think of stuff like that. But when PCM's here, this stuff just becomes blindingly obvious, and people are going to have to tackle it. But people are doing exactly what you're saying today, right?
Can you say anything about why battery back here is expensive? Because it seems like, I mean, is it, I can get a big battery, that's fine, at some expense. But relative to PCM, I mean, PCM doesn't exist, battery back here is cheaper. I mean, are there logistical problems that you guys, like practical problems with building large battery back DRAM systems that kind of make it really impractical, not just from a cost perspective?
I don't know. Yeah, I don't know how impractical it is per se, right? We don't build our own; we buy it, we buy it. But DRAM is very power hungry, and so it depends what kind of window of failure you're prepared to tolerate, right? So on a filer, if a data center loses power, and we've got dirty buffers, we don't want to. We're prepared to tolerate 24 hours without seeing power again. Now that limits the size of the DRAM that we can actually attach a battery to.
But like, how much? You write sequentially to a disk that's a single one is at 200 megabytes a second. Like it doesn't take that long to persist in terabytes of DRAM out an array of disks.
Well, how often do you want to persist in a terabyte?
I mean, certainly you could persist it within the 24-hour time frame you said.
Oh no, 24 hours without power. Not 24 hours till loss of power. 24 hours without power.
I think in 24 hours you probably could persist hundreds of terabytes of DRAM, right?
Without power?
Well, if you have
I think I've
If you had
lost there.
batteries, yeah, if you had batteries, that's what I'm saying.
Okay, if you have I mean, then you're talking about a generator, right?
No, UPS, like, that could, I mean, for several hours, probably, you could persist a good amount of DRAM at one time, right?
Oh, sure, but you have to do that. Are you going to do that for your entire data center or just a particular machine? You put a UPS just for one machine in a data center, you've just increased costs a lot. Because a human being's got to manage that.
Okay. I mean, I guess you gotta replace the battery and make sure it works as
Yeah.
well.
But people are, I don't want to belittle your point because people are doing exactly what you're talking about, right? SAP HANA, for example, they're keeping an entire database in a terabyte of DRAM. They are doing these things. It is happening. Okay, so what's happening, in the application world? Well, initially, disk access was, for example, the IBM disk I showed you earlier was, it was record-oriented, and languages like Fortran and COBOL, actually incorporated that kind of functionality directly inside the language. In 1974, the SQL paper was published. In 1979, Oracle started selling the first commercial implementation of SQL. But basically, up until 1999, if your working set didn't fit in memory, because the previous discussion assumed that the entire working set was in memory, but if your database doesn't fit in memory, and that's most databases, well, your choice was a table or a table. In 1999, that changed. MongoDB introduced the notion of actually storing things in column order. And actually the motivation was memory bandwidth, not disk bandwidth. And then in 2006, Michael Stormbaker, roughly the time Michael Stormbaker published a paper called The System's Broken, It's Time for a Complete Rewrite, or whatever, blah, 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 blah. He argued that domain-specific databases beat the pants off of these two guys every time, so let's start writing domain-specific databases. And, people started doing so, and there was a massive explosion of new databases. And I can't even touch the surface I can't even scratch the surface of what's going on out there. So for stuff like this is kind of old. I call it old school. There aren't that many new airline reservation systems being deployed, on a daily basis, right? American Airlines has their system, and they're not going to change it. And they use relational stuff, right? Banks are very conservative for certain things, right? Your bank accounts and stuff like that. They're very well taken care of. It's usually on EMC boxes, VMAX. Financial companies and hedge funds, they do all sorts of crazy stuff. They don't necessarily all use relational stuff. But then you get into stuff like, say, HBase, Cassandra, CouchDB, and Cassandra, right? I mean, is it a database, or is it a storage system, or is it both? It's really starting to blur the line there. And what you were talking about, you got SAP HANA here, Oracle times 10, you've got Microsoft's offering as well, and these are entirely in memory. And they offer very, very interesting storage workload characteristics, right? SAP HANA, and it's in memory, right? So it never reads. It never reads. It's all in memory. It never reads. It writes out a transaction log. It also writes out what they call safe points, but it never reads, except in the case of disaster, in which case it wants that 1 terabyte of data off disk and back into memory as quickly as possible. Otherwise, it never reads. And all the algorithms that go inside a storage device that are optimized for making certain that a certain read performance for random I/O, etc., is maintained, they've been obviated. No one really cares. And this is going to get even more interesting when these kinds of applications start living in SCM. And there's just tons more of it. How people build applications is just completely different now. You've got platform as a service. If you've got the next Facebook in your head, you're going to open an account on EC2 and start building your application there. And look at there's just 10 million different kinds of applications with 10 million different kinds of workloads. Can one single storage system, the general purpose storage system, is it fit for purpose any longer? That's just really unclear. The days of just, I'm going to deploy an Oracle application. Oh, okay, well, you need this kind of volume, and you're done. That just doesn't happen anymore. Or just write a COBOL application. It just doesn't happen anymore. So this puts tremendous pressure on storage devices. So, here's an example of Amazon, right? So here's a page. What actually goes into this? They use a different application for almost everything you're looking at. And the question, and so, they have their own storage system, so they have solved all these problems. But if you were doing this with something like a NetApp filer, right, can one storage device deal with all these different behaviors? The question at the moment seems to be no. So there's an opportunity here, right, for specialized storage devices and specialized storage services. And I think it's very fruitful for research. What's next? Why didn't it change? Okay. There's been an explosion of protocols. The days of just implementing iSCSI, NFS, and CIFS and being done with it, they're over. We just can't keep up with all the storage protocols being offered, right? And they're also incredibly simple. I mean, one of the values that NetApp had was in implementing NFS4 correctly. It's a complicated protocol, and it's got to be done properly. So people will pay money for an NFS4 server that's been done properly and highly optimally. But no one cares. A lot of people that don't care about that anymore. S3 is the simplest protocol in the world. A monkey could implement it. That's one of our value adds potentially gone, right? Back in the last decade, NetApp spent over $300,000 at least fixing the Linux IP and NFS stack just tired of the support calls, and it was always the same problem in the Linux stack. So we just paid to make it work properly. But stuff like that, no one cares anymore. One customer even said, NFS is evil. He said there's nothing particularly wrong with the protocol per se. It's a fine protocol, but the fact is that if he's writing an application in the cloud and needs to migrate it out of the cloud or back into the cloud, he's not going to get NFS in the cloud. He wants something like S3. That's the only protocol he's interested in, because that gives him the mobility to go in and out of the cloud and move around the cloud. Okay?
Do you think that this is a persistent problem? If you look back at the origins of NFS, there was NFS, and there was Andrew, and there was Sprite, and there were all these other different file systems that were distributed, and they had a lot of the same characteristics as NFS. And then we just sort of, whether it's on a merit basis or not, we chose one. And now everyone uses NFS if you want for a while. I mean, is this just a flurry of diversity that's eventually going to sort of condense down to, is going to be S3 or something else? Or is this a persistent state of affairs, do you think, where we are now in this, is there a fundamental technical reason to have this kind of diversity?
Well, so I think to go back, let's deal with NFS very quickly. Right, I think NFS took off because it was just so simple, right? The research landscape is littered with the corpses of distributed file systems, and none of them, really ever made it commercially. NFS is it's a point-to-point, goes easy, and S3 is even easier. So I think a lot of it is just, it's just easy. Read and write objects, it's easy to implement, and so I think it took off, right? The Amazon guys could have, used free NFS clients, but they wanted something simpler and easy. And it's so easy, I think, that you can just keep writing it for whatever application you happen to be building. If some kid in a college dorm is writing the next CouchDB and writing the protocol is fun, they're going to do it. And so I don't think this is going to converge to one thing. I think this proliferation is going to continue, which leads to all sorts of problems for manageability and all sorts of stuff. But I think it's going to continue. Because these aren't coming from standards bodies. IP, TCP, NFS, there are strict RFCs dictating what, how these are to be implemented, et cetera, et cetera, et cetera. A lot of this stuff has no RFC, right? People just going out and doing it. It's the hippiedom of the internet. It's, stick it to the man and just do their own thing. Oh God, we're running out of time here, so let's just go through this very quickly. Okay, so software-defined storage. I don't really consider this software-defined. It's not really what I have in mind, but I was mentioning earlier, right, that for NetApp to sell disks, we have to add value in the form of software, right? Snapshots and all sorts of disaster recovery, blah, 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 blah. But what's actually happening in data centers are these frameworks are emerging where an application specifies its requirements, usually declaratively somehow. Some cloud orchestrator is just supposed to go out, find the storage for this application and provision it, blah, 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 blah. Here's an example of OpenStack, right? So, the orchestrator decides to provision a VM, so it gets the storage from here. So we actually had to write drivers to work with OpenStack. But it's not clear how we can expose our snapshots and our other value add to the applications, because it's all hidden. In something like OpenStack, it's the lowest common denominator that is being built, which isn't good for someone like NetApp because we have expensive storage with lots of features. But if those features are being masked by OpenStack, why would you buy our expensive hardware? You're just going to buy a white box. So I'm just going to burn through these now quickly. I'll just say something very quickly here. Nowadays you quite often find private data centers and And public data centers and an enterprise will actually be using both, and so that leads to questions of how do you move data back and forth, what are the caching policies and stuff like that, and you have to incorporate economic arguments, right? Because it's not just latency or the hotness of data, it costs money to read it, it costs money to write it. You have to bear that in mind. These are very fruitful areas of research still, despite lots of work being done. Software-defined networks. I think this can have a huge effect on the upcoming storage infrastructure, right? I just mentioned distributed storage systems earlier. There are very few actual genuine distributed storage systems on the market or in the world. They're hard to get right. And stuff like EMC Isilon and NetApp cluster mode, some of the value that those systems add is whatever features they do have, they got it right. And so people buy those products to get those features that are leveraged. But if somebody writes an SDN controller for storage that handles high availability, handles caching, and handles all this other stuff, people can just use that and use a white box. So there's a value add that NetApp has potentially lost. What do we sell in this environment? And I'm sorry, I guess I'm officially over time now. This is important. Who cares? I will do. Okay, I'll just go here quickly. So this is the world that we're looking at the moment, right? We've got applications, and we have an appliance. But are all the IOPS going to take place here in an SSD or other host-attached flash or PCM? If so, you're not going to buy expensive 15K RPM disks from us, right? We're going to be a capacity tier. And that's far more cost sensitive. What's the protocol going to be that's going to go in here? This network, if it's a software-defined network, what features that do we normally implement here, they move out here, that's value add we've lost there, right? If we're in an OpenStack type framework, what functionality can we expose to keep adding value so we can charge our margins for our hardware? So the landscape is very uncertain in the coming years. And I will conclude there. I apologize. I actually meant to leave 10 minutes for QA, but